is our first speaker is Professor Dr. Carlos Amendola, and he will talk about the Gaussian graphical models. And he is discussing today some it's like a tutorial session. So what he has just discussed in first two lectures, he will propose some problems and then.
Yes. Yeah, thank you very much for the introduction. Yeah. Yes, so I have a couple of exercises that I want to put on the board, and I would like for you to try them. And yeah, so that they will be, work maybe together a bit, look at the notes from the past two lectures to try to remember the definitions and the properties. And after, I don't know, maybe 25 minutes, half an hour, I would then come back to the board and maybe explain a bit, give maybe hints towards the exercises. I want to discuss a bit more to give you more tools in order to solve them for the last part. Okay, so that's my plan. So, okay, so tutorial. So the first exercise, it's gonna be, we have a three-dimensional random vector that's distributed multivariate Gaussian, mu sigma. And just for the sake of this exercise, I'm gonna assume that sigma is a bit simpler than just a general sigma. It will be what is called a correlation matrix. So a correlation matrix has ones in the diagonal. So these are rows. Okay, so row 1, 2, row 1, 3, and row 2, 3. And okay, for a first question, so part A is what is the conditional distribution? X2, X3 given X1. Okay, so we defined what it meant to have a conditional density. And the question is, well, in this case, what would be X2, X3, given that X1 equals some little X1? Okay, then part B, show that X2 is independent of X3, given X1, if and only if there is a condition on sigma, namely that row 2, 3 equals row 1, 2 times row 1, 3. Okay. Then part C is compute the concentration matrix. And remember, this was K, which is the inverse of sigma. And the question is, well, what do you observe? I mean, after computing, in the context of B. So like assume that X2 is independent of X3 given X1. Is there anything special happening in this concentration matrix? And then finally, the last part in this exercise is to prove that if X2 is independent of X3 given X1, and X2 is independent of X3, if both things happen at the same time, then X2 will be independent actually of the whole vector x1, x3, or x3 will be independent of x1, x2. So this is actually a special case of the so-called Gaussoid axiom, which Thomas really likes. I don't know if he's there somewhere online, but yes. So I'm just gonna write the special case of the Gaussoid axiom, whatever that means. Right? So you should think about there are matroids. So I hope you like matroids. So matroids, the analog here would be the Gaussoids. So there is some system of conditional independence statements and implications that have to hold for Gaussians. Okay, so I think this would be part one. And maybe then let me write the second one here. So for each of the following directed graphs, so I'm gonna give you a few graphs. So well, the first one, well, actually it's like the 0, 1, because I kind of ended the last lecture with that one. So and I kind of already gave what was the answer, but maybe it's a good exercise to actually do the computations and check. And then it's good because you actually have the solution if you look at the last lecture. So this would be the 0th one. Then the actual first one, which is new, will be this. So I'm numbering them. Then the third one is going to be fourth one is going to be this one. And one last one in case you're done with the other ones. This one. Okay, so these are 5 graphs plus 1 extra. And well, so what is the task? Well, part A is to label the vertices from 1 to m using a topological ordering if possible. Okay, so you need to name them. I didn't give them numbers. You have to choose your labeling. And if possible, you would like this to be a topological order because we saw that had nice properties. Okay, so B will be write down the linear structural equation for the Gaussian graphical model associated to G. Then part C is going to be compute identity minus lambda inverse. right? So here in part B, there will be a lambda that you'll find. So now I want you to compute identity minus lambda inverse. And even more, just instead of just computing, can you interpret its entries? Right, so like we look at these entries and maybe can we see some pattern there? Can we understand how they appear? Okay, then part D would be compute the explicit parameterization of the model, which would be sigma in mg. And the same question as before would be, can you interpret these entries? Okay, so again, this question. And finally, part E, the last part. Would be the hardest one in a sense, which will be to actually compute the ideal, the vanishing ideal. So compute IG. Okay. And the question again will be, can you interpret these generators? And so maybe let me already give a couple of hints on towards what kind of interpretation one should be looking for. In this one, maybe one should be looking at the graph and the directed paths in the graph or the paths in the graph. And for this, maybe you should try to interpret these generators as determinants or subdeterminants of sigma. Okay, so that's going to be my hint, right? So maybe there are some determinants appearing, determinants of submatrices of sigma. Okay, so yeah, these are the two exercises I will invite you to try. For this one, I wouldn't necessarily go for like each one and go all the way. You can try, for example, to do part B for all of them first, which maybe it's easier, and then then start to go down towards these ones only after you finished A, B, C for the other ones, right? That would be my suggestion. And yeah, so I'm going to be here, and if you have any questions, I'm happy to help you. And as I said, so my plan is like maybe, I'll give you some time to work on this. I hope it shouldn't take that long. And maybe after some 20 minutes or so, I would then come back to the board and then tell you a bit more of the hints of how the solutions look like. Okay? Okay, then let's do it like that.
Said sigma is a correlation matrix.
Yes.
You
So
want to say something about EIGs?
sorry, what was the question?
OIGs?
The rows? Yeah, so the rows are just the entries of
Not between -1.
they are between -1 and 1, yes. But this is a consequence of sigma being positive definite. Right? So there is a nice observation. So the rows, they are correlations. So that means, very good, they will be between -1 and 1. But this is automatically, I don't need to say this because sigma is positive definite, right? So for example, the first 2 by 2 minor, the principal minor, is 1 minus rho 1 2 squared, right? And that has to be positive because it's a positive definite matrix. And then so that means that then the row has to be between -1 and 1. Right? So if you look at this, oh yeah, maybe that was not good. Let's do this. note, 1 minus rho 1, 2 squared is positive if and only if absolute value of rho 1, 2 is less than 1. And yeah. Okay, so yeah, I'll